Hey guys, welcome to this third video on reinforcement learning and MATLAB. In the first two videos, I went over what reinforcement learning is, some basics of Q-learning and what environments are, and also I showed you how to import the OpenAI gym environments into MATLAB and also apply some random policy to it. So in this one, we will solve our first environment. So the environment that we will take here is the same as the previous video, which is the mountain car. So it is this environment, and we will be solving it in MATLAB completely. Now, solving here means that your agent, which is this car or cart, is able to reach its objective, which is this point, right? So the point for this cart or car is it has a fixed acceleration. So it has a maximum fixed acceleration. So if it starts moving in this direction, it'll be able to reach just this point or something like that because there's gravity as well. So the way it can solve this problem, it can go up, it'll reverse itself, put its velocity in the other direction and try to climb this and just gain momentum that way, and then finally it'll be able to climb this hill. So, so this is how we will solve this, or this is how our reinforcement learning algorithm will solve this challenge. Now, solving an environment typically means finding the policy. So, finding the optimum policy. So, a policy takes in your observations. That means it takes in your states, your current state, and gives you what is the best action to take at that point. So, um, in our reinforcement learning example, the cart will give out its current position and velocity, and it'll tell us what action to take. So this is the game for us. And the two observations are, like I said, cart position, and it goes from -1.2 to 0.6, and then we have car velocity, which goes to from a fixed amount to a fixed amount, from negative to positive. Now, there are three actions that we can take. Either we accelerate to the left, we accelerate to the right, or we don't do anything. So it's a discrete set, and we need to take these three actions. So given the position and velocity, what action do we take is what we'll try to figure out. And the thing is that you receive a reward of 0 when you reach this flag, but you receive a reward of -1 if the agent is not at this point. So at every time step that you're not at this point, you receive a -1 award. So there are a total of 200 steps for an episode. So this episode will go on for 200 steps. A single step is agent tells you its position and its velocity, and you figure out what the action you have to take. You take that action, and then that's the next time step. So you can accumulate a maximum of, or rather a minimum of -200 points. So anything more than that is better, right? So if you achieve your goal in say 100th step, so if you reach this point in about 100 steps, that means your total reward would be -100, which is better. So that's the task, and the initial position is around uniform random value in in this regime. And yeah, so that's pretty much it about the environment. Now, the way we will be learning or the way we will be performing reinforcement learning is by doing Q-learning, which I already talked about in the previous video. But just a quick reminder, this Q function takes in a state and action, and it outputs a certain value. For so for example, it'll take in the position and the next action, or say it takes in the state. So here the state is position and velocity, and then it takes in an action, say 1, and it'll give you a number. Now for all the three actions, there would be, so for a given state, you would have three different values for the three actions, and the largest Q value tells you which is the more optimum action. So that's how Q value works. Now to learn the Q value, you have to first do this iterative process where you take in the old value and then you see the reward that you received and then multiply it by add a discounted next step reward to it and then subtract the old value. I talked about this in my previous video, so have a look at it. But I don't want to go into details of this. But in this video, we will see how to solve this in MATLAB. So since solving this would require a lot of scripting, I have already written the script. So we will just go over the code in this video and I'll just run it and I'll walk you through what's going on. So let me bring this up here. So give me one moment to figure things out. Okay, great. So here I have a live script which solves this environment. Now I will go over this code and I will also upload this code on my GitHub page and I will add a link to it below in this video description. So first of all, we begin by setting a random number generator seed so that our results are reproducible. Then we take in this environment like the previous video. I define a learning. So now I define the hyperparameters. Now let's go back and see what were the things in our equation. So alpha, the learning rate, is a hyperparameter. The discount factor is a hyperparameter. So these are two that you immediately see. So that's why this is the learning rate and the discount factor. Learning rate is alpha. So these are the two parameters that you see immediately. Now, episodes is how many episodes do I want to train my agent? So I just gave it 25,000. Display frequency tells me this is a variable I use to show every 1,000th episode. So I don't want to see all 25,000 episodes. So just show me the 1,000th episode. And then here, the next couple of lines are pretty important. Now, like I said, the position space goes from minus 1.2 to 0.6. Now, between these two values, there are infinite number of points, right? So, and I possibly can't contain all of them. So the way you do it, the way you go around it is you discretize your space into buckets. So I'll say that anything between 1.2 to 1.1 would be counted as bucket 0. 1.1 to 1.0 is bucket 2. So I just make discrete buckets because just to make my learning quicker and also to save on memory. That's why, and I would do the same thing with velocity. So I have buckets of 20. You can play around increasing this value to higher or lower. And then I divide my observation space into this buckets to see what's a single bucket value is. Now here I take the highest value of my observation space and subtract by the lowest value. So that gives me the whole range of values my observation space can take, and I divide it by the number of buckets I have. So it gives me how much values, what's each bucket size. Now I'm using the same bucket size for my position and velocity. Okay, so that's one important thing. Now the next four lines have to do with exploration. The way a reinforcement learning agent learns in the beginning is that it does a lot of random exploration. So in the beginning, your agent has no idea, you don't have a policy, so you don't have no idea what's going on. So you want to do some random exploration. And these are the four parameters that control that behavior. So I start with an epsilon. So I'll tell you what this specifically does, but it's something that begins at 1 and then it decreases. So basically 1 indicates that a lot of exploration. So the higher epsilon is, the more exploration would be. So it starts with 1 and then I decay it by a certain amount. So the way I decay it, I set decay should begin at episode 1 and the decay should end at episode 12,500. And how much it should decay by, I divide epsilon by the difference of these two numbers, and that's how much I decay it by. So basically that's how it's supposed to be. So this basically controls the exploration, and I will show you how it does that. Now, now we create our Q table. Since this is a discretized problem, our action set is just 3. So, and our buckets are 20, 20. So I just created a matrix of size 21 times 21 times 3. And I basically rescaled my values and fill this table with some random values. And this is not so important. You can create random values whatever way you want it to be created. So um, let me run this bit. Great. So oh, I got an error that conversion to single from NumPy array is not possible. Hmm. Let me debug that. Give me one moment. All right, yeah, sorry about that. I realized that I had Python 3.9, which was having some issues, so I reverted back to Python 3.8, and that seems to have resolved the issue. So, another thing I've learned, use Python 3.8 for now with MATLAB, or at least when you're using Gym. So yeah, so let me run this block again. And as you can see, the buckets are of size 0.09 and 0.007 for velocity. And our Q table has been created. Okay, so now let's come to the meat of this discussion where we will train our Q learning, or rather learn our Q table. The way this works is first, so we will loop over 25,000 episodes. So this is the major for loop. And inside this for loop, there is a while loop, which basically runs till the episode is over. So till the episode is not done, or we have taken 200 steps, either of those. Okay, and whenever we start an episode, we first reset our environment. And notice that whenever I reset my environment, when I get my current state, I pass it through this function, get disk state. So this is a helper function that I have at the end, which basically, so let me just go down. Okay, yeah. So this helper function, basically what it does is it will take in the state and return the discretized state. So basically now, instead of all those decimal values, your states will be the bucket values, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, onwards to 20 for both position and velocity. So this helper function just gets you that discretized state back. Okay, great. So we get our discretized state over here, and then we start looping over. Now, this is the thing that I was talking about, the exploration. So what we do is we generate a random number between 0 and 1 if that number happens to be greater than epsilon, right? So epsilon was a parameter that we selected over here. If that number is greater than epsilon, what will happen is we take the action from the Q table. So what we are doing is we take the maximum of Q table values. Now, if you remember, the Q table has 3 dimensions. The first 2 dimensions indicate the state, where the first one is the position, second one is the velocity, and the third one is the action, right? So here I'm taking the maximum of all for a given current state. So I'm passing in the position and the velocity, and then I leave action as is, like basically figure out which action gives me the maximum Q value. I'm not interested in the maximum value, but I'm interested in the argmax, or which particular index, which means the action over here is the maximum. Okay, so this is what happens. Else, take a random action. Now, now since the random number is being generated between 0 and 1, and we start with our epsilon being 1, right? So this condition more often than not is not met because whatever random number you generate would be less than 1, or even when it becomes 0.9. So the possibility of this random number being higher than epsilon is quite low in the early phases of training. So in that process, in that case, a random action is taken. That's how we promote exploration. And after this episode is done, here we till my episodes is between the end and decay, sorry, beginning and end episodes of my epsilon decay stage. I keep on decreasing my epsilon. So my epsilon keeps on reducing from 1 to a lower value after every episode by this decay value. So basically what's happening is that I'm reducing my exploration as I keep on training my agent. Great. Now, okay, so we've found out the action. Now I step in the direction of that action. The int16 is here because it's between the MATLAB and Python conversion of data types. I pass a cell because this environment returns a tuple, and that's why cell is how I would contain those in MATLAB. Okay, so that's that. This condition tells me is this episode number, should I display this episode? And that happens when it's a multiple of 1,000. So if you remember, I set the display frequency to be 1,000, so display every 1,000th episode. So that's why I will only render it when it is divisible by 1,000. The episode number is divisible by 1,000. So once okay, so that's that. Now, since I've stepped in the next, since I've stepped according to the action and I've gone to the next step, I can get the exact state from this cell array. So this is what I'm trying to get. I'm getting that discretized bucket state again. I get the reward, and I also so here's I'm just keeping a tab of the cumulative reward of each episode, and then finally there's another flag that tells me whether an episode is done or not. So I'm just keeping track of that or not. Now, um, right. So this is the main step of Q learning. So let me get this equation here as well. So right, let's see what's the best way to do this. Right. So in this update step, I first need the old value, right? So the first thing is the old value. Then a learning rate is multiplied to this reward, and this whole thing is being added in. Now, the current value comes twice. So there's the current value plus, or rather, if I take this part together with this part, I get 1 minus the learning rate times Q. So that's this term, 1 minus the learning rate times current Q, right? And then what's remaining is the learning rate times reward. This is the reward over here, plus discount times the maximum of future Q. So this new underscore Q line is this exact equation. Okay, so let me repeat that again. So I take this thing and this thing together. So that's 1 minus learning rate times current value of Q plus learning rate times reward plus the discounted maximum future Q. Okay, so that's the equation. Now let's look at the terms. The current Q is basically what is the current Q value, and I can just quickly figure that out by putting in the current state and the action we just took um, in that, and then just read off the value from the Q table. So that's that. The maximum future Q is basically find out for the next state that you got, which action, or rather, what is the maximum value among all the actions. So basically I do a max and I leave the action as blank so that it searches through all the possible actions and gives me the value of the next maximum action that gives the maximum Q. So once I have that, I just update my Q table. So Q table, and then So now the next state is the current. So for the current state, I pass in this new Q value because the current state gets updated. So that's all that happens. And also, I need to pass in the condition that if I've reached the final point, so the final point would happen at around bucket 20, um, the value is 0. And the reason why I set this value to be 0 is at, because this particular action at this state gave me the um, ends the wins us the game and gives us 0 reward. So just set it to 0, and then I just put in the done flag. So this is basically how Q-learning works. And then at the end, I just basically keep a track of all the rewards I got over all the episodes, and then I close my environment out and then plot the reward. So yeah, I know that's a lot to unpack over here, and let me run this bit. So soon you will see. Let's see if uh, builds. So yeah, so it'll first plot out um, our environment only at the 1000 step. So let me get that window over here. Okay, here. So every 1000 step, this window will get updated as to what the agent is doing. So give it a moment. I obviously will not make you guys sit through all 25,000 episodes, and I'm gonna fast forward this bit. So that's what the agent is doing right now. So I'm just gonna pause the video and start recording once it's done training. So right now we're at like around 15,000 episode mark, and I just want to show you what the environment is doing, or rather how much it has learned. And it took just like a couple of minutes on my 6-core processor. Yeah, this whole training is being done on CPU. So as you can see, it has learned to just, swing back and forth to generate momentum, but it still hasn't figured out how to solve the environment yet, but I'm sure it will soon find that out. Let's wait for another render. That's another 1000 episodes training, so it's learning quite a lot during that duration. That failed miserably. Let's wait one more. Yeah, it is definitely very time consuming and also requires a lot of trial and error. Ooh, it almost made it. I saw it reach this point. It was pretty close to it. So it's getting there. So the way in Q-learning works is that like the rewards get propagated back to different states. So the reward from finishing the goal or reaching the goal gets propagated back all the way to all the states. Oh, finally. As you saw, our agent finally made it across. So um, great. All right, so I'll now skip ahead to when the training is done. Great. So the training is over, and our agent has learned how to solve this environment. And here you can see a plot of, which is a pretty horrible plot of how the rewards look like. So initially the rewards were around minus 200, and now they're like roughly stable around minus 110. So the agent is able to solve this environment is in about 110 steps. So great, we've learned how to solve this environment, and then now we can just test it out. Now we don't need to modify our Q values anymore. All we need to do is select the action. So we can just run this, which for some reason it always loads up in a different window for me. So let me do this. 0.1. All right. I'm just trying to load in the window. Let me just give me a minute. All right, yeah, I finally figured out how to get the window on this screen, and I added a pause for some slow motion effects, and let's now test in our environment to see how it does. So I do that, and you can see how it's. Well, let me play that again. So you can see first it builds up momentum to reach the state. So okay, let's maybe add some more pauses. All right, so let's yeah, so let's try this again. Okay, great. So it goes up and back and up and down. So great. So yeah, so we were able to solve this environment, and that's how Q-learning works. So we were able to solve our first environment in MATLAB um, using nothing else. You did not need deep learning toolbox. You did not need the reinforcement learning toolbox. Now, keep in mind, this is a very simplistic environment, and we used very simplistic Q-learning. As the number of state grows, so here for our Q table, the number of states is 20 times 20 times 3, which is like what, 1200. But then as the number of state grows, um, Q tables become cumbersome, slow to learn, they take a lot of memory. That's where you would need to use deep reinforcement learning. So basically, instead of just doing this discretized Q learning, you would be doing Q learning with neural networks, and that's the fun stuff. And that's where the reinforcement learning toolbox also comes in. So in the next videos, I will talk about that. Also, I would like to give a big shout out to Syndex from pythonprogramming.net. So he wrote a very simple uh, Python script to solve this particular environment, and my MATLAB code is basically an adaptation of his Python code. So big shout out to him. And this was a very hard video to make with all the technical difficulties and whatnot. So, but I hope you enjoyed it, and I hope I helped you learn something new. As always, this code will be uploaded on my GitHub page, so you can find it there. And thanks for watching this video. And go ahead, like and subscribe it, please. It helps me out. And also, I have made a deep learning tutorial for MATLAB as well. So have a check that playlist out as well. So all right, so it's been what about 30 minutes. So I'm gonna end this video now and see you in the next video.